layer, but not in the z direction within each layer. Does that make sense?
How is it about the 2D system? Why is there a z direction?
So the system to imagine is, okay, we have a wavy interface between two layers. And up here, there's only one flow speed. And down here, there's only one. And this slope actually governs the difference between them.
Yeah.
Right? But within this layer, we have uniform density, so there's no horizontal gradient. So in thermal wind balance anyway, there's not any shear.
Yeah.
And even in the shallow water limit, even if there was the possibility of shear, it wouldn't arise naturally on its own, as long as you remain hydrostatic.
In the inflection point theorem, which is the y direction? What are you talking about?
Yeah. So that's that's the orientation for this problem. And in the inflection point theorem, where you say, I don't know, write it however you want. Flow, this direction is y, this direction is x. In the inflection point criterion, there's no gravity. It's 2D without gravity and without stratification in the Rayleigh method of writing it anyway. In this version, there is always gravity because you have thermal wind and a bunch of other pieces going into the quasi-geostrophic form. Does that make sense? So if I threw away one of these layers and just solved for the upper one, I would get the inflection point criteria back. So if I looked for the equivalent barotropic by setting the motion in this layer to 0, I would get that Q1 d by dy of Q1 had to change sign to have an instability if Q2 had no velocity by assumption.
What is the asymmetry between x direction and y direction? Why are we looking at the y derivative instead of?
Because we have assumed that Q is a function of y and z only. It's plane parallel flow. So this is the direction across, and this is the homogeneous direction in the initial conditions. That's the only difference in the F-plane version anyway. In the beta plane version, you actually could have another symmetry breaking because you could say there was a north direction or an east direction. And this formulation says that y has to be north-south, essentially. Does that make sense? Is everybody following that part? So, until you say what the mean flow is, you don't actually know which direction is x and which direction is y. The x direction is aligned with the mean flow, and the mean flow is only allowed to go in one direction because, by assumption, because it's plane parallel flow. So that's what makes all of the integrals, all the extra terms in that integral, the VQ term, disappear, is because of the assumption of plane parallel. Okay. All right. So, well, let's go back. So what is it? All right. So I wanted to briefly touch on this before we move on. So, why was I showing these videos in the beginning? Now we have delved deep. Like when I took GFD, doing linear instability calculations was like 80% of the class because it's something you can do in class. It's something that you can just crunch, and you start to get a big handle on the relationship between stream function and vorticity and all of these relationships. But what's the flaw in doing that?
Mostly stuff is not linear.
mostly stuff is not linear. So these two examples that we talked about, vorticity is really important in a fluid. That's probably a pretty linear system. That's definitely not. Right? That kind of vortex merger is a strong, we could have said that the rings at the beginning were just rising under a steady buoyancy force and they were traveling at relatively uniform speed. That would have been a linear vorticity advection. That's not a linear vorticity advection. But you have some sense that that's important for turbulence, like that kind of process. And over here in the boundary layer, there's really nothing that's linear. You might say that the shape of the instabilities in the beginning, the size, the spread between them might have had something to do with the linear instability. But you can see they're merging and they're overturning and they're breaking. All of this kind of phenomena is stuff that's not described by the linear system. Why not? What's the quick way to decide that those kind of things can't happen? There's a large Rossby number, so that's part of it. That's the reason why it's nonlinear. But what happens in a breaking or a merger that violates our particularly Fourier transform approach to solving these equations?
The modes aren't independent.
The modes aren't independent. So different K's and L's and sigmas are interacting with each other. This is, you might have said that there was one particular, if you did this in polar coordinates, it would have been easy to say there was one particular distance from the origin. But now there's one little one and one big one, and it's wobbling in the other direction. It's definitely not staying in one mode. And on this side, you can see that there's, when they merge, they're changing smaller things and bigger things, particularly in this direction, because they start out, uniform, L equals 0, and then they break, and when they break, then there's maybe two structures per domain, which is L equals 1, in the right normalization, and then that breaks again and becomes L equals 2, 3, 4. So that kind of breaking and interaction stuff is not allowed in the linear system where the Fourier modes are independent. So waves where Fourier modes are independent, or linear instabilities where Fourier modes are independent, is not a good descriptor of the scale-to-scale connectivity that's in a turbulent flow. Does that mean? So we've learned about it. We think it's helpful for getting started because it gives you ideas like, hey, the growing modes are going to be roughly the deformation radius and size in a QG system. That's really important. And if they're bigger than that, they'll have more potential energy. And if they're smaller than that, they'll have more kinetic energy. Those kind of guidelines are helpful to come out of the linear theory. But now the exchanges of potential energy and kinetic energy from scale to scale is what we're going to use to break into the nonlinear system. Okay? So these are just the subsections of what's in Vallis's book. We're just going to talk about these little pieces today. We're going to start into the spectral theory, and then we're going to transition a little bit more into phenomenology of ocean turbulence by next week. So we'll look at the first few chapters in Thorpe, which talks a little bit about what's turbulence like in the real world and all that kind of thing. So Thorpe, you can access it through the library. There's on the syllabus, there's an URL that if you click on it and then log in with two-factor wherever you are, it'll take you there. And if you're on campus, it just goes, I think. So you can look at that. It's not very long and it's not very hard to read. It's kind of pictures to think about and stuff. But this week we're going to talk about particularly the dimensional analysis aspect of spectral theory. And then we won't touch we'll just touch on the beta plane. This is for large-scale turbulence, stuff like storms in the atmosphere. We're mostly thinking about smaller scale stuff, so we'll primarily focus on these three pieces. But first, we have to get to why we even want to think about turbulence and what the issue is and how it relates to our linear theory and why that's different. So one of the most one of the worst kind of puns and word twisting, but things that's most important to think about when turbulence is, we like to break things flow into the mean part and the turbulent part. But in order to do that, you have to decide what you mean by mean. So what do we mean by mean? There's lots of things we can mean by mean. So what kind of average, so we want to break up a flow, and this is using velocity, which is sort of the traditional place to start, but we could equally have done it with temperature or with potential vorticity or something else like this. Actually, potential vorticity is an interesting case, which Abby is writing a paper about. But anyway, so we talk about having a mean part and then a deviation from the mean. So what kind of average does that make? What kind of average might you think about? And what does that imply about what's left over? So what's a temporal mean, a time mean? What does that say? That's sort of like our basic state in this case. Our basic state was independent of time, and that allowed us to do some things. So the growing modes in this where would the growing modes be classified in this? In the prime part. And in fact, when we did the linearized equations, that's the notation that Vallis used. He didn't use bar like this. He used capital U, but then he had U prime or Q prime and stuff like this. But we could continue and go beyond the linear instability and start thinking about the nonlinear equations, V times V. So that's where we want to go with turbulence, is to think about that part. What about the fact that the Q here is independent of X? Does it stay independent of X? The mean flow part? The background flow just is independent of time and independent of X. So instead, when this thing starts wiggling like this, we can take any deviations and put those into the prime category. And in fact, in the linear instability, that's what we almost always did. We had something that was like e to the ikx plus sigma t. So the time varying part and the x varying part was totally inside the perturbation. V-twiddle is what he calls it. Something like that, right? And V-twiddle was a function of y. So would the y average be a useful kind of average? In this problem, this kind of setup? The mean flow also changes with y. So if we had a shear in this direction, it would not be terribly helpful to say I define the mean as the average in this direction, because then the average has removed that variation. Or if we had a difference between the two layers, we wouldn't want to take the z average flow as the mean flow, because that would miss that shear in the initial conditions. So how physicists describe this is they say there are homogeneous directions. This flow is homogeneous in x, it does not vary in x, and it is homogeneous in time. And so either one of the averages, the x average or the time average, would be an appropriate definition of mean. But you don't want to take a direction that it's not homogeneous in as the one that you're going to take as the average. Does that make sense to everybody? That would just tank it. It's not that it's impossible, it's just that it's not clear why you're doing it as far as defining a mean. Okay, so that's temporal and spatial. What if the mean flow actually has no homogeneous directions? It's like the real ocean, which has time variability because of seasonal forcing and diurnal cycles, and also kind of wiggly currents and weird coastlines. Then what do you do? What's the turbulent part? Think about it from the perspective of repeating an experiment. If we repeat an experiment multiple times, which part is the turbulent part and which part is the not mean part?
The turbulent part is like the non-replicable part.
Yeah, so this is closest to how Reynolds originally thought about it, is he was doing these pipe flow experiments, and the flow down the pipe was the same every time because he was setting it up with a gravity drop from one end to the other. But he noticed that this kind of chaotic motion would happen. He couldn't explain it, but he said, what if I just repeat my experiment many, many times? And there's a random part I have no control over, and then there's a predictable part, which seems to be the same every single time. So in fact, let's define that formally and say the mean part, the mean over many experiments, is the mean, and the random part is the rest of it. Does that make sense to everybody? And so that's called an ensemble average. You can do it over repeated experiments. In a numerical model, it's really easy to do it. If you think the way that Akash has been working on, if you change the initial conditions slightly, just a tiny amount, you won't change the large scale flow very much, but you'll change all the turbulent bits. And the turbulent bits then would be different each time, but the forced response is the part that's responding to the large scale structure of the basin and the large scale forcing directly, not the instabilities and then the nonlinearities on those instabilities, would be similar from system to system. Does that make from an initial condition to initial condition? So in that sense, we might call this the climate and this the weather, and that this is the one that's sensitive to initial conditions, but this is the one that's structured. Or we call this the internal variability, this the forced variability. So there are a lot of different related concepts hiding inside of this. Does that make sense to everybody? Okay, and then the last form that we want to think about is what if we just take a low pass filter? So if we don't have the capability of doing an ensemble average, what if we're just doing observations? We can't go back, but we might think that the slower, steadier stuff was more mean than the less slow. The fast stuff was more turbulent. And you can be formal about that if you make this assumption that what we mean by bar here is a low pass in space and time filter, and you go through the equations, you can actually find that there is like the leftover bit has a stronger nonlinearity since it tends to be smaller in distance and smaller in time. So how can I think about that from u dot grad u? How does this object depend on spatial scale? If I just scale it, how does it scale?
U squared by n.
U squared by L. And we don't know what U squared is like. It actually is also a function of scale, which is where we're trying to go, to figure out what function of scale that might be. But let's just assume that the energy in the small scales and the energy in the large scales was about the same. Then which one is more nonlinear? Which one has greater nonlinearity in it? It's the one with the smaller scale. This term gets bigger the smaller the scale gets. Does that make sense to everybody? Okay. So you could use a low pass filter hoping that the low pass part was more linear, more easily predicted, and then the high pass, the stuff that goes by, would be more nonlinear and more turbulent. Is there an interaction between the small scale stuff and the large scale stuff, or the ensemble mean and the... Should there be? Does the small stuff affect the big stuff? Fast stuff affect the slow stuff? Does it in this problem? Why not?
Linear assumption.
It's the linearity in this problem that prevents it from feeding back. So we're going to see that in just a second. One great example of linear versus nonlinear and filtering versus averaging is daylight savings. So we just had it yesterday. So there are health consequences of daylight savings because people tend to have heart attacks more today and yesterday because they've gotten one night less sleep, which is kind of shocking. And in the fall, people don't have as many fewer. So on average, between the two, you would lose because the spring one hits you harder than the fall one relieves you. Does that make sense? So there is some issue in that, and that's closely related to one of the issues with the low pass filter. So suppose I have an anomaly like this. If I filter this and look for the low, what if this is a Gaussian, say? Does everybody know what? Well, I don't want to go too far into the Fourier transform. Let's just talk about low pass filter. What would happen if I put this through a low pass filter that was kind of similar to its filter width? To its amplitude. Everybody has a sense what does everybody know what a low pass filter is? So in Fourier transform space, if you have some energy as a function of k, we're going to get more detailed about this. So this is the scale, this is the energy. The low pass filter, you basically throw away the high k stuff and you keep this stuff over here. And a simple way to do this is to take a Boxcar average, which is a sliding window in time. So if you have your signal, you average this part, then you move it over, you average this part, then you move over this part, and so something that's really spiky gets down to something smoother when you put that sliding window on it. But both the spiky part and the smooth part depend on every single point in time. It's not like the x average here, which was once you've taken that average, now you can't go back. You only have the average and it doesn't depend on x anymore. Or if you want to write it this way, the integral of the signal d time divided by the integral d time. So if I want to take the total time average, I could go from 0 to infinity in both. And that would be my v bar, total time average v bar. But if I want to use a smoothing filter like this, then I would use t minus some interval, t minus some interval. So this is like a smoothing filter that gives me an average. Okay? So what happens if I do that Boxcar filter on this? What happens when if my filter, sorry, let's put this, let me leave this in axes, make this slightly. If my box touches into there, I get a little bit of it, right? So I get something like this. It'd be a little higher than the original signal because I'm touching into this a little bit. And when I'm here, it's not quite as high as this one because I'm also averaging it with some lower stuff here. So I get something that looks kind of the same but would be a little squashed down. All right. So here's what a key concept for what the difference between a Reynolds average and a filter, which is something we're going to come back to over and over again. Once I've taken the x average here, what happens if I take the x average of the x average? It's the same thing, right? So if I'm writing the average from 0 to infinity of, signal of x dx over the integral from 0 to infinity of dx. If I do this again, the first time I do it, it's no longer a function of x anymore. It's just whatever. It's not a function of x. If I do it again, this goes in there, and I just get v integral over integral. Those go away. So I get the same thing. So if I repeatedly average the average, I get the average. That seems ridiculously stupid. But it's not, because what happens if I average this equation? If I average this side, what do I get? V bar. If I average this, I get, or if I average both of these, what do I get? Is averaging a linear operation? Yeah. So that means that I get the sum of the average of the first term and the second term. And what's the average of the average, if this is true?
The average.
The average. So I have the average equals the average plus the average of the prime. I can subtract that over, which means the average of the prime is 0. Does that make sense to everybody? So this is almost so obvious that it's not obvious that it's an assumption and that it is not true of all of these possibilities. In particular, the filter, it is not true of. Because what happens if we go past and filter the dashed one here? What do we get? Is it going to be the same as the dashed one again? It's not. It's going to be still a little bit smoother than last time. And if I average it again, it gets smoother still. And if I average it again, it gets smoother still. So in the filtering case, this is not true, which means that this is not true either. So these means are all different. This one is useful when we're homogeneous in time. This one is useful when we're homogeneous in, say, x. This one is useful if we're not homogeneous in either, but we still want a Reynolds operator. And this one is what you use when essentially all of those fail and you don't have a Reynolds average. You have to do something a little bit more different. Okay? So in modeler speak, we talk about this one being a temporal average, this one being a spatial average, this one being a Reynolds average, this one being a large eddy simulation. So they lead to different sets of motion and different ways of treating turbulence between those. Okay, so we still haven't gotten to why the nonlinearities are hard. Maybe we should just, what if we just try and calculate how much the nonlinearity is? So this is a nice example that Vallis boils down. So he says, what if we take ddt of a variable with some nonlinearity in that variable and some linear damping? So R doesn't depend on U, it's just a constant. Okay, so if I want to write down this equation, I can't do it because it's nonlinear, it's horrible. So what if I try and use this trick and write down an equation for the average of this? If I average this equation, and the average is not a time average, so that I can bring it inside the ddt, then I get the average goes with this and with this. So if this was the equation, I'd be set, right? The solution would just be a linear solution. And if I was in the linearized system like this, this would have been 0. This would have been weakly, we would have assumed in the linearized system that once we took this, we threw this away, right? Because we had used linearized system. But in the nonlinear system, this term is there. And it might even be bigger than the other terms. In fact, it's kind of easiest when it is. So what do we do about this guy? How do we handle that? So there's one theory of how to do this, which is called Brad Marston likes to call this the method of cumulants, which is what they call it in condensed matter, but in turbulence it's more serially called a higher moment closure. So what if we write down an equation for a UU bar? We can do that. How do we do it? Well, we take this equation, we multiply by u, and then we get 1/2 ddt of u squared plus UUU plus RUU. We take the average of that equation and we get this. ddt of UU. Great. We're solving for this one. And we know how to do this. That's also depending on the same thing. Great. We could solve that equation. But now we've got one that's got 3 in it. So what if we take the one that's got 3 and we write down an equation for that? We're going to get 4. If we write down the one for 4, we're going to get 5, and so on. So in the beginning, it looked like this bar prime decomposition was going to help us get somewhere, but it really only helps us get somewhere if we can manage this term. So if these are the slowly varying things and these are the fast things, what is this term telling us about? So u bar, which we could write as u bar plus u prime bar times u bar plus u prime, which we could write as u bar bar plus 2 u prime u bar plus u prime bar. Okay, so if this is an average quantity, this is an average quantity, and taking the average of the average, what do we get? If it's a Reynolds average, we would get this one would be u bar. Because once I've taken the x average, if I take the x average of the x average times the x average, I still just get the x average times the x average, right? What about this one? It's 0. Goes slower though. If I take this part is say the x average, then it comes outside of the average because it doesn't depend on that x. Then it would be the bar of the prime, because if that comes outside, then the prime goes to 0. So that would be 0. Okay, if, we'll put that, all right, it's our key caveat. And then what about this one? We don't know anything. And what does this tell us if we're thinking about small, fast stuff going to large, slow stuff? This is the term. This is a small, fast thing. This is a small, fast thing. But it's appearing in an equation for the slow thing. So this nonlinearity is coupling the different scales together. So in the linearized system, this was exactly the term that we neglected. It comes back, and it is the coupling between different scales of motion. If I wrote this out as, sine kx, if I was thinking about it that way, I would get sine of 2kx, sines and cosines, sorry. I'm not going to do the trig identity carefully. But you get the sum and the difference of these plus something that's constant, which is the difference part of those. Sorry, is that clear to everybody? If this was e the I kx and this was e the I kx, I'd get the pluses and minuses, and then we cancel across. So I'd have the sums and differences of the wave number that would come out in the product of the two. So the one that goes from small fast stuff to slow stuff is the one that appears back in that equation. Okay. So this was an abstract example. Yeah.
First and the third term, they are two different terms, right? Which are in addition.
This and this.
So can they evolve differently or something?
They can. So suppose we were using a time average. This one would not vary in time, but it would be important to get it right. Oh, sorry. This one wouldn't vary in time because this doesn't vary in time, this doesn't vary in time. But it's an important part of the flow. So like, if all the currents are concentrating repeatedly into one region, the concentration, the doubling of this would be an important term in that budget for energy or budget for momentum. This term, this was varying in time, this is varying in time. Their product might have a component that's varying in time much more slowly, or might have just a part that's steady. But so this is the wiggling parts, the waves and waves interacting together to produce something that doesn't vary in time.
And we cannot talk about their order, so they might be of the same order.
Yes, making approximations about how big this one is versus this one is one approach that people take a lot, and that's a helpful thing to do. So the Taylor's frozen turbulence hypothesis is essentially about the relative size of these two things. So you can make progress by assuming that, but there's no reason to, since we can't close this budget, we don't actually know that it's going to be small. It's kind of like it just keeps going. And in strongly turbulent flow, it actually tends to diverge, that the higher moments become more and more important. So it doesn't get easier. This term is bigger than this term. Not always and in the ocean and the atmosphere, frequently this term is actually pretty modest in comparison to this, which is why we can still see the deformation radius. Because if this term is still there in a weakly nonlinear case, but this one is only a strongly nonlinear, this is the one that's making scales talk to each other. This is the one where the scales are talking to each other, but less so. So the preservation of the original instability scale tells you something about kind of how big this correction is versus this one, and this one versus this one, and so on. If those corrections are really big, you would lose that scale information. Where we observe that that's not the case. So that tells you a little bit about those flows. But in a strongly mixed lab flow, that's definitely not the case. All right, I'm going to skip over this. I think we already said this. Okay. So less abstract. What if we write the momentum equation? We play this game. Here's the momentum equation, v dot grad u bar. When we take the average, we get this one and we get this one, if it's incompressible. Sorry, so we can bring the v inside. So this is the, if it's incompressible, I can write v dot grad u equals v u. Then I take the bar, which equals v bar u plus b prime u prime bar. So this is the b prime u prime bar, this is the other one. And so this thing is a divergence of something, which each component has a velocity from this part and a component of the velocity from this part. So this is the amount of momentum transported in the turbulence by the turbulence. And you can't create or destroy momentum, so it has to be inside an overall divergence, which is good to see. This means that if you integrate over the whole world, this thing goes to zero and the momentum is conserved. But if from point to point within the fluid, the turbulence could be concentrating it over here, separating it out over there, reducing momentum, increasing momentum, mixing it around. So this object, this is called the Reynolds stress tensor, or this is one component of one column of the Reynolds stress tensor. The divergence of the Reynolds stress tensor is the momentum impact of the turbulence in an incompressible flow. Okay? But if we think about it, it's just a bar, 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 prime problem. Here's the bar, bar bit. Here's the prime, prime, bar bit. Here's the average of the flow. So we're seeing kind of how things go. All right. I'm going to skip over this part. We'll talk about this next time. But I want to leave you with one thought. So if different scales of turbulence are interacting with each other, do we think that the kind of scale interaction is different in geostrophically balanced flow, or things that are sort of like geostrophically balanced flow versus 3D turbulence? I'll just remind you of this little movie. So here's the non-rotating movie. So what kind of motion is natural if you take a constant density fluid and you stir it like that when it's non-rotating? It'd be just kind of disordered 3D stuff, right? There's no Taylor-Proudman theory, there's no stiffening. And so what's happening to those things? You start with this little squirt, and then it spreads out to a blob, and then the blob does what? It has little fingers. So would you say that is it big things causing littler things causing littler things? Like, look up here. So all these little things. So it's kind of there's definitely an interaction between things of different sizes, right? It starts at one size, it gets to a different size, and then there are little fingers of other sizes coming. So if you wanted to try and describe that, it would be an interaction between different scales, right? Everybody's on board with that? What about in the rotating case? Let's wait till they squirt it. Is this an interaction between different scales? Is it the same interaction between different scales as we just saw in the 3D case? Definitely not, right? It's qualitatively different. One thing that it does is it becomes very large in the vertical. It just saturates and then it moves like a block, right? That's the Taylor-Proudman theorem. So that's telling us that in the vertical, you're not going from large scale to small scale. You just sit at the whole depth. Those phenomena are that. And then these are very long and skinny instead of blob-like. And so we're going to need a metric for something that has energy in it. There's flow, but energy in narrow things instead of energy in blobby things. And so our game as we go into turbulence is going to be to try and quantify the difference between these two and make predictions for how the interaction between different scales occurs. In this quasi two-dimensional case, which is also a quasi geostrophic case except for the little inertial oscillations, versus the three-dimensional one, which has a very different kind of turbulence. It's blobby instead of streaky. So that's where we're going. And when we get there, we're going to find out that both kinds of turbulence are important for the atmosphere and the ocean on different scales, because why? Rossby number is different, essentially. So when the Rossby number is small, we get stuff that looks like this. When the Rossby number is big, we get stuff that looks like the other one. And so as a function of scale, we have qualitatively different turbulence on large scale and small scale. All right, cool. And so you should have gotten the peer review thing, and the key I posted last night. And so the next homework isn't due until after spring break. So this is the last little piece of stuff for a while.